And today I'm going to talk about the first results of NA62 in the beam dump mode. So my name is Alina Kleimenova. I'm currently working in Bratislava, and I'm an NA62 member for some time at this point. So let me introduce you to NA62 as well. That's basically an overview of my talk. And let's start with the overview of NA62. So NA62 is a fixed target experiment. We are located in the north area of CERN SPS. And the main goal of NA62 is to measure the ultra-rare Kaon decay, where Kaon decays into pi plus nu bar. And so for this we use a novel technique in this kind of series of experiments. It's a Kaon in flight technique. And there is quite some motivation to measure this decay precisely because it's known very well theoretically, as you can see here. However, our previous experimental value was pretty far behind with respect to precision compared to theory. And the NA62 took the goal to measure it as precise as possible. Original plan was to measure it with 10% precision. And we produced our results in this paper in 2021 with the full run 1 data-taking data analyzed. Apart from the pi nu, we have a rather broad physics program. So we also study other rare forbidden Kaon decays, but also we search for exotic particles in Kaon decays and in the beam dump mode. So let's have a look at NA62. So in NA62, the detector was designed to measure the pi nu bar, and you can see that it's pretty much reflected in its apparatus. So NA62 uses proton beam from SPS, which is 400 GeV protons, and they hit beryllium target and produce secondary beam, which is unseparated hadrons, from which 6% are kaons. And so these kaons and other particles, they travel to NA62 apparatus, and since we want to know the Kaon, we have a detector which identifies the Kaon, which is called K-tag. And then we measure the momentum of the beam particles with GigaTracker. And basically, after this, the beam travels inside the vacuum, vacuum volume, which we call decay region. And we study the decays of Kaons which are happening inside here. So the decay products are then measured in straw spectrometer and identified by rich detector, LKR colorimeter, and we also have MAV Vito detectors which are placed at the end of the beam line. Important to notice here that the vacuum tank is surrounded by the large angle Vito detector, which we call LAV. It's basically a colorimeter. So to achieve our goal with pi nu, we had to achieve these performances, and in fact, we managed to do so. And this kind of performance is also good for any other search that you do in NA62, basically. So this is how we operate in the standard mode, in the Kaon mode. And now let me introduce you the beam dump mode of NA62. So in this case, we basically remove the target. And after the target, we actually have this copper collimator, like copper and iron. And when target is removed, you have all these 400 GeV beam hitting this collimator. And here I put a little bit small cartoons to show you like normal data taking compared to the beam dump mode. And in this case, the beam just basically stopped inside here. And of course, you can produce a lot of different particles, including say channels, Alps, and so on. So this is what I mean by the beam dump mode. Now, to give you a closer picture, this is how NA62 looks like. We already, as I said, took some data. We actually started in 2014, and we had several physics runs. In particular, we had last year, and I will be talking about the data collected in 2021. And right now, we're collecting data, and we expect to do so for some time. So, yeah, basically on this picture, I put a few detectors so you could see and try to recognize from the scheme, and the target is over there. So, just for the information, since I will be talking about the beam dump obviously has dedicated trigger streams for its data taking, and it has mainly single track, two track, and control trigger. So the single and two track, they're based on charge hodoscope detector, and yes, so these triggers we will be using in the analysis. So let's come to the main topic of the talk. And we have a lot of motivation to search for the new physics, and we studied in particular in this case the vector portal, which is the dark photon. The dark photon is the simple extension of the standard model, which you introduce, where you introduce the vector field, which then couples via kinetic mixing to the hypercharge. And in this kind of model, the mass and the coupling are free parameters. And so one can compute the branching ratio of dark photon into the standard model particles. And I show the plot on the right-hand side. So you can see actually that below 600 MeV, the decays of the dark photon are dominated by leptonic mode. And we actually focused for now only on leptonic modes. So let's see what NA62 can do with the dark photon. And in NA62, we looked for two production mechanisms. One is Bremsstrahlung, and another is meson-mediated production. So we studied pi 0, omega rho, and eta, actually. In 2021, about which I'm talking about, we collected 1.4 times 10 to the 17 protons on target. So now we can assume this number of protons, and only leptonic decay modes of the dark photon, only geometrical acceptance of NA62, and no background present. We can put upper limits, and I show you on the right-hand side two plots separated by top plot is separated by the production mechanism, and bottom plot is separated by the decay mode. And from the top plot, we can see that actually the dominant our production mechanism is basically the direct, what we call direct, but it's Bremsstrahlung production. Unfortunately, we're going to present today only the mu mode, and so you can see that in this kind of scenario, we have at best this green dashed curve. Obviously, in the plants, electrons are present, so in the end, we will try to do everything. Okay, so how did we do the analysis? The analysis basically focuses on lepton-anti-lepton pair. In current case, it's mu plus, mu minus, and we reconstruct the vertex within the NA62 decay volume. Then we require the vertex to be pointing back to the interaction point, which is at the collimator. And so obviously you apply event selection, and importantly here that we require no in-time activity in the large angle Vito detectors, because that helps to reduce possible interactions of incoming particles in these detectors. So, and of course, in the end, we define the signal region. Signal region we define in the following way. So on the right-hand side, I show you a plot, which shows you the propagated vertex, which is propagated back to the interaction point. And then you compute the intersection point between the beam line and the vertex, and you find the z position of this point. And you can see that this is a signal Monte Carlo, and you can see that signal is peaking around 22 meters, and this is where tags are. So the y-axis here are actually closest distance of approach, which is also computed at this point of, say, yes, closest distance of approach. So it's basically measures the distance to the interaction point from the propagation. So the signal and control regions are defined in this parameter space, and the precise values are shown on the slide. So during the analysis, we kept both regions blinded, so we opened them only after the analysis was approved by the collaboration. So what do we see in data? And it's interesting to see using the distribution of track time difference. And so on this slide, I show you on the left-hand side, it's a signal mu plus mu minus before love veto is applied. And you can see that there are two components to this background, which is around 0, so in time, and the combinatorial background. So that's the in-time background is actually due to interactions in these love detectors. And when you apply this love veto, you basically end up with something like this, which is a pretty nice result, given that here I don't show you the control and signal region. But it was not always like this, and for this kind of background, we have to thank the beam group who worked hard to optimize our beam line. And here you can see the comparison between 2018 data taking before the optimization of the beam line and the 2021 data taking. So you can see that this is much less of POT collected than we have now, but much more background than we have now. And again, for this, we thank the beam group. So let's continue on with the analysis. And it's important to discuss what our expected yield. And for this, we use this kind of expression, which includes our protons on target, the probability of producing a dark photon and probability to decay, and probability to reach the fiducial volume of NA62 decay there. And finally, we accounted for the signal selection acceptance, geometrical acceptance, and the trigger efficiencies. And here on this slide, I show you the selection and trigger efficiencies separated by the production, and the expected yield separated again by production. And you can see that in case of acceptance and trigger efficiency, we have a dependence on the mass and the coupling in both cases. And you can see that we have actually different acceptance values for different productions. And in the end, as expected previously, you can see that the expected number of events is, of course, dominated by the direct production in this case. So, and of course, for the analysis, it's also important to measure the mass resolution, because we want to know where to look, how to do the mass scan. And so basically here I again separated by production mechanisms, and you can see that our mass resolution has dependency on mass and on coupling again, and also on the production. Now let's talk about the background. And as I talked about it before, we have combinatorial background and prompt background. So the combinatorial background is just a random combination of two muons, which are coming from the beam halo, because you still have some particles coming out from the tags. And so since computationally it's pretty complicated to simulate the beam halo, we used data-driven approach, and in this case we selected single tracks in data in a different trigger sample compared to the analysis, and then we artificially tried to superimpose track pairs, applied the same event selection criteria in the analysis, and obviously in this case each track had its own weight to account for the rates and to account for the trigger downscaling and so on. And so the results of this will be shown on the next slide. But what concerns the prompt background is even more complicated to do than combinatorial. And in this case, we used, say, hybrid approach, data plus Monte Carlo. And in this case, we have basically background originating from the secondaries of the muon and other particle, beam particle interactions in the material of our detectors, mainly love. So in this case, after studying Monte Carlo, we observed that actually this background is really negligible in comparison with combinatorial, and therefore on the next slides I will be focusing on the combinatorial background. So to validate our technique, we use several control samples, and in this slide I'm showing you two control samples that we saw. It's mu plus, and mu minus. And so the color, basically the shades, this comes from our data-driven approach, our, say, Monte Carlo. And you can see that in these tables, I show, yes, the black dots on the plot is data. And basically in these tables, I show you the numbers that we see outside control region, so everywhere, inside control and signal regions for both of these scenarios. And you can see that agreement is pretty nice in both cases. Now, if we have a look at the signal sample, here we were acting more careful, and we selected not just control region, but several control regions to validate what we see. And basically, here I show you how many events we expected and how many events we observed inside each of the control regions. And this is our expectation for the signal region. And the probability, this is important, the probability to observe one event or more inside signal region, we estimate it is about 1.6%. Now, since we trust what we expect, we opened the signal region. And what we observed one event, which actually accounting for global significance is 2.4 sigma. However, you must note that we didn't account for the signal shape, and you can see here again the signal Monte Carlo compared to this observed event, and it's quite unlikely to be the dark photon signal. So for the future, obviously, it would be nice to take into account the signal shape. So now if we say about final preliminary result, it would look like this, obviously not as good as I showed previously. And since the event was observed in 411 MeV, you can see the limits a little bit worsening here. But otherwise, that's what we've got now. So that brings me to the conclusion, and today I showed you our first results in the beam dump mode, and we do a lot of analysis in the beam dump mode, and this is the first result. And we analyzed the data of 2021, but we are collecting more data, and we are obviously, we want to collect about 10 to the 18 protons on target by the 2025, and we continue our studies, so stay tuned.